Okay, I will continue to present about the SQQPK. Okay, this project applies the operation engineering principle to optimize the two case study. The first case study is about the smart home lighting product design by Luminotech. Luminotech using critical path method to optimize the week schedule and evaluate the parallel task executive. Next, the analysis demonstrates how strategy scheduling improvement. The second case study is about the green tech electric vehicle factory construction. This case study examines the 21-month electric vehicle factory project to lean construction and fast tracking lengths, proposing mitigation strategy for regulatory, technology, and schedule constraint in sustainable industry construction. Okay, let me continue with the introduction. First introduction about smart home lighting product design. Smart home industry require repair product development cycle. Luminotech is lighting system with motion detection and app control phase scheduling influence across 5 sub-project A to E. Okay, the second introduction about green tech electric vehicle factory construction. Green tech is Penang factory represent a 2 billion sustainable manufacturing investment with government deadlines and automation complexity. The project requires optimized schedule, maintaining green building. The problem statement in the first case study is sequential task dependence create unnecessary delays, followed by supplier selection sub-project E occur late in development cycle, and the last is resource conflict arise when multiple teams require overlapping engineering expertise. Okay, the second problem statement of the case study is tight 21-month timeline with 13 interdependent phase, and the second is high risk concurrent activity, and the third is unproven integration of lean principle and mega project scale. Moreover, the project objective of the first case study is reduce the total project duration. The second is optimize supplier engagement time without compromising design feasibility, and the third is develop a resource leveling framework for parallel task execution. The project objective for the second case study is identify a mitigate 5 highest impact construction risk, and the second is evaluate the ROI of automation and traditional labor approach, and the third is develop the fast tracking protocols without the compromising safety. The scope of the project in the first case study is CPM analysis of 15 core activity. Second is evaluate two alternative structure, where is inter sub-project parallelization and supplier process integration. And the third scope is execute the detailed cost analysis of market testing. Okay, the second scope of the project is focus on civil construction and production line installation. Second, a comparative analysis of 3 lean construction techniques, and third is excluded vehicle R&D and post compromising operation. First contribute in the first case study is demonstrate the duration reduction potential. Second is framework for balancing concurrency risk in hardware and software development, and third is decision metric for resource constrained product. Okay, the second contribute of the project for the second case study is prioritizing the framework for greenfield electric vehicle factory. Second is quantify 17% scheduling reduction potential through optimize the fast tracking, and third is best practice for lean automation synergy in Southeast Asian context. Next, I will passing to the second presenter.
My name is Ku Jen Yu and my matric number is 299511. Next, I will explain the methodology used in our project. First, for the data collection, all necessary information was taken from the two provided case studies. This included the smart home lighting product design and the green tech electric vehicle factory. Both cases provided detailed activity list, duration, and dependency which form the foundation for our analysis. Our research process began with extracting the activity and identify the relationship between them. We then created activity on node, which is AON diagram, to visualize the flow of the project. Using this diagram, we calculated the earliest and latest start and finish times and identify the slack for each task. This allows us to find the critical path, the sequence of the tasks that directly determines the project duration. For data analysis, we use the critical path method to make our calculation more accurate and efficient. We use QM for Windows software. This tool helps us to generate network diagrams, calculate scheduling metrics, and test different project scenarios. By comparing various scheduling options, such as running tasks in parallel or merging activities, we are able to evaluate not just time efficiency, but also how these changes might affect coordination and resource use.
So for the case study 1, we managed the smart home lighting products design for Luminotex. We use QM for window apps to construct the activity on node networks or LN diagram shown here. The arrows show the order in which the task must be completed. An activity can only start once all its predecessors activity are finished. For example, you can see that after A4s, 3 parallel tasks begin with B1, B2, B3, and E1s. The visual layout helps us quickly identify which activities are done in sequence and which can be carried out simultaneously, making it much easier to schedule and manage the projects. We use QM for window apps to generate this diagram, ensuring that all dependency and relationships for the case study are accurately represented. Next, for the question 2, this table summarizes the project schedule result for all activity in the smart home lighting products design. For each activity, we show the yearly start, yearly finish, late start, late finish, and slack. This value will be calculated using QM for window apps. Based on the activity duration and dependency from the case study, the ES and EF column tell us the sooner each activity can begin and finish, while the LS and LF columns show the latest they can occur without delaying the projects. Slack indicates how much flexibility we have for each activity. For this output, we see that the minimum duration for the entire project is 20 weeks, which is determined by the critical path from start to finish. This table helps us identify which tasks are urgent and which ones have some scheduling flexibility. Question 3, we identify the critical path, which is the longest sequence of activity with no slack, meaning any delay on this path will delay the whole project. For this case study, we actually have 3 critical paths, all of which must pass through the major sub-projects, which is A1, A2, A4, B1, and then go through either C1, C2, or C3. After that, D1, D2, and the last E3. It's because all 3 activities, C1, C2, and C3, take the same duration, which is 2 weeks, and represent different ways to develop key components in the projects. Having multiple critical paths show that the project is tightly scheduled with little room for errors. For the question for slack and non-critical activity, I show a table and we highlight all activities that have slack. The slack tells us how much we can delay an activity without affecting the project overall completion time based on the table calculated using QM for window apps. We see that activity A3, B2, B3, E1, and E2 all have possible slack. For example, A3 have 2 weeks of slack, B2 have 10 weeks, and B3 have 11 weeks. This means these tasks can be rescheduled or delayed by their slack time if needed. without causing any delay to the project as a whole. Identify this non-critical activity is important for effective resource management and risk handle during the project. Moving to question 5, parallel team scenarios, we look at what happens if each sub-project's team can work on all their activity in parallels instead of in sequence. This means that for each sub-projects like A, B, C, D, and E, all activities start together and the duration is only determined by the longest single activity in that sub-projects. Looking at the tables, for example, sub-projects A's longer activity is A2 at 3 weeks, so sub-project A only takes 3 weeks to finish. We apply the same logic for each sub-projects, taking the longest task from each. Adding up these durations sequentially, the total project's durations become 3 plus 4 plus 2 plus 3 plus 3, which equal 15 weeks. This scenario shows how running tasks in parallels, when possible, can significantly shorten the overall project timelines compared to doing everything in sequence. For question 6, merging supply selections, we consider what happens if we merge the supply selections activity E1 and E2 into sub-projects A as a new activity A5 with a duration of 4 weeks. This new activity is scheduled to run in parallel with A1, A2, A3, and A4 at the same time. Sub-projects B and E are completely removed from the projects. Looking at the table below, within sub-projects A, all 5 activities now run at the same time, so the duration for sub-projects A is determined by the longest task, which is A5 at 4 weeks. After sub-project A is complete, the project continues with sub-project C, where all 3 activities is C1, C2, and C3 can run in parallels, so this phase only takes 2 weeks. Finally, sub-project D has 2 activities, D1 and D2, that must be done sequentially, so taking a total of 5 weeks. By summary up these durations, 4 weeks for sub-projects A, 2 weeks for sub-project C, and 5 weeks for sub-project D. The total minimum project durations under this new structure is 11 weeks. This shows that merging activity and allowing more works to happen in parallels can greatly shorten the overall timelines, provided enough resources are available. For question 7, we evaluate this change using 2 non-time-based criteria, resource constraints and coordinations. Doing more activity in parallels or merging responsibility increase the demand on staff and can overload team. It also makes coordinations more complex, raising the risk of mistakes. For future projects, Luminotech should ensure that have enough resource and strong project controls before using this approach to balance faster delivery with quality and reliability. For case study 2, we developed the LN network diagram using QM for window based on table 2. Each circle is an activity and arrows show the order of work. For example, after node I finish, both J and K start in parallels before merging again at L. This diagram helps us easily see the project flow and where tasks can overlap. Next, for the question 2, we're using QM for window and calculated the yearly start, yearly finish, late start, late finish, and slack for each activity. The table shows the minimum total project duration is 25 months, driven by the critical path, which is start from A, B, D, E, F, G, H, I, K, L, M, N, and the last is O. Any delay on this path will directly delay the project. For the question 3, activity C and J can be delayed by up to 0.5 months and 1 month respectively without affecting the overall project completion times, while all other activities must be performed as scheduled to ensure timely project delivery. For question 4, we identify the several key risks that could affect the construction and launch of green tech EV factories along with practical mitigation steps. For example, delay in regulatory approvals are a concern, so early engagement with authority and regular follow-up will help keep the process on track. Likewise, unforeseen site conditions could disrupt progress. Therefore, conducting detailed site survey and preparing the flexible contingencies plan is essential. Supply chain disruptions also pose a risk, which means green tech should identify backup supplies and maintain the safety stock for critical materials. Finally, to address the potential labor shortage, it's important to plan the workforce in advance and build a partnership with local training providers to ensure the necessary skill levels. By managing this risk proactively, green tech can better ensure that the project is delivered on time and within the budget. For question 5, we explore the benefit and challenge of applying a lean principle and automation in building the EV factory. On the positive side, lean automations help reduce the waste and minimize the unnecessary process, while also improving the resource utilizations and overall efficiencies. They can shorten the construction timelines by streamlining the workflows and enhance the safety by reducing the risk of human errors. However, there are also important challenges to consider. They include the high initial investment needed for automations technology, as well as the requirement for staff training and careful change management. Moreover, integrating these new systems into existing constructions practice can be complex, and there may be a potential resistance from workers or contractors who are not familiar with the change. Because of this, while lean and automations offer major advantage, they also demand truthful planning and support to be successful. For question 6, we look at what green tech should consider if they decide to fast-track the project by overlap some activity. First of all, careful coordination is required to ensure that any shared resource or workspace do not create conflicts or bottlenecks. In addition, detailed planning is necessary to identify which activity can be safely overlapped without compromising quality, safety, or compliance with regulation. It's also important to remember that overlapping activity may increase the risk of error, rework, or miscommunication, so effective communication channels and regular progress reviews should be established. Lastly, the cost implications should be analyzed, as fast-tracking may increase the expansion due to overtime, expedited procurements, or potential inefficiency. Overall, green tech should balance the potential time saving against this risk and determine if fast-tracking is appropriate of the project.
To conclude the presentation, here is a brief summary and our recommendation. We analyzed 2 case studies using project management techniques such as the critical path method and scheduling analysis. We explore how different scheduling strategies like parallel execution and activity restructuring can affect the overall duration and complexity of a project. With the help of QM for Windows, we were able to carry out accurate calculations and assess different scenarios effectively. Based on our findings, we recommend that project teams use scheduling tools like QM for Windows and Microsoft Project from the start of the planning phase. This helps in testing alternative plans and improving efficiency. It's also important to consider not just time but also other factors like workload distribution, communication, and risks. Therefore, applying a structural planning approach like this can lead to better results and more successful project execution.